Alright, so here we go. So today I continue to work on ECS in ZIG. Yep. This is the current state I have. Honestly, it's kind of weird. Like I don't really feel how can I do that, right? And I feel like I lack a lot of knowledge, understanding of the system, you know? How should it be implemented? So that's basically the approach I have right now, right? Yeah, so basically it's a bunch of arrays. Where is it? Yep. So we got components, and then I'm doing multi-array lists of components, which basically makes similar structure. The problem are these gaps, right? And I don't really like them. I use Gemini to come up with a simple, efficient way to implement it, but it's still kinda difficult for me. Let's actually just write it down to Gemini, like basically everything I struggle with. I want ECS and ZIG learning pose, but I really struggle with what? How do I describe it? Is implementing it, but with understanding how to do it, how to what? Do it correctly? I don't know. Could you please help me get better? Learn about how can I implement ECS in simple yet efficient way. I guess pretty good. Run. My light is way too bright, I'm not gonna lie.
Hey, I'm kind of glad you didn't.
Yeah, that's better.
I kind of just called to hear your voice. I miss you. I've been thinking about you. I've been thinking about our love. And how much.
Just like that. Let's break down. Build a simple yet illustrative ECS. We'll prioritize clarity and understanding first, and then discuss how to make it more efficient and generic. Nice. Our goal is to create an ECS. Hello, Faris. Hello. Привет. How are you doing? No, like, it feels unfair. It feels unfair. Wait. French. What am I doing? Bonjour. Great, how about you? I'm good. I just came back from my trip to my friends, to Poland, and trying to implement ECS in ZIG, which, like, I don't know, for some reason is kinda hard for me. So basically I'm just prompting Gemini to explain me how to do that. Like, do you know ECS, right? You probably know this. Entity Component System. Such a cool thing. So our goal is to create ECS that is easy to understand, demonstrates the core principles, uses some of ZIG's powerful features. The core concept, the what. First, okay, entity, yep, component, yep, raw data, a simple struct in ZIG, it has behavior, no methods. It has no behavior, no methods, examples. Yep, system, the logic, a function that operates on entries, yep. That's I know. The simplest implementation strategy, the how. The hardest part of CS is managing the data. Where do we store the components and how do we link them to the entity? So, we got this world, but it's kinda confusing, not gonna lie. For our simple model, we'll use a strategy that is very easy to reason about. Entity ID is as array index, yeah, but then we got gaps in arrays, right? So that's what I'm doing right now. Basically, I got components, which is a struct of all components, and then I'm doing multi-array list. So basically, it's just an array for each of these field. But that means, like, if I'm gonna add entity which has only one component, all the other components gonna be null, and they're gonna be gap, and that means, like, space is not gonna be used efficiently, right? Plus, I'm not sure how can I, like, if I'll remove the entity in the middle, what should I do next? Like, should I, after creating a new entity, should I put it instead of the whole, or should I add it to the end and just ignore the whole? I'm like not really sure. Okay, entity ID is an array index. Okay, optional components will have one big array for each component type. To handle entities that don't have a certain component, will make the array element optional, yeah, just like I do. If we have position and velocity component, our world, the main ECS container, will look like this. Okay. If entity 5 has position, the world will be position struct. Yep. Pros of this approach: super simple to understand. Getting a component for an entity is a single array lookup. Cons: waste memory for the null values if components are sparse. Iterating through all entries with a specific component set requires checking every single entity, which can be slow. Yeah. But for then, this is a perfect starting point. Let's build the code. Entity. I mean, it's called entity ID, but who cares? Position. I got transform. Oh, I got vector. Yep, velocity. Actually, no, let's make it float. World container. Allocator. World allocator next entity ID. This one is confusing. Positions, velocity, player text. Core world functions. Init, return world. Okay. The init, okay. Create entity. Const entity equals self next entity ID. Okay, self next entity ID plus equal 1. Okay, so it's okay. Adding and getting components, the comptime magic. Wait a minute, but isn't it like... It's like the part of the world, isn't it? It's a field. How can we modify it? How do we write a single add component function that works for position, velocity, etc.? We use ZIG's compile time features, anytype and comptime. Inside pub const world struct, public function add component, entity, component, void, const type of component, comptime, t position, self position items, entity component. I see. Okay, so we create an entity, right? With null everywhere. And then we just add component to the current entity. That means we can operate on one entity at a time, right? Which is kind of bad. What if I want to add... I mean, maybe I'm just over-engineering it way too early, right? We can use similar pattern to get a component. We return a pointer so we can modify the component in place. Entity, comptime, t-type. If t equals position, we have custom with the optionality. Oh, okay. Explanation of comptime. This is a key of making ECS usable. Instead of forcing the user to call world positioner, we provide a clean API component. The comptime block ensures this is done with zero runtime cost. The compiler effectively copy-pastes the correct code for the type you provide, yeah, right in the systems. So basically iterate through everything. Entity ID. Yep. Get component, yep. Put it all together in main, okay. How to improve it, the next steps. This implementation is simple and it works, but it has the efficiency problems we mentioned. Here's the learning path to make it better. Problem memory waste and slow iteration, our released, yep. Our system loop, chicken, yep. Solution, sparse sets. What are sparse sets? How are they different from sets? How to do the following operations efficiently if there are larger number of queries for them: insertion, deletion, searching, clearing, removing all the elements. One solution is to use self-balancing binary search, tree like red black tree, AVL tree, etc. Time complexity of this solution for insertion, deletion and searching is O log n. We can also use hashing, like hashmap. With hashing, time complexity of first three operations is O1, but time complexity of the fourth operation is On. I mean, it's good, I guess. Sounds like the best option. We can also use a bit vector. Oh, it's like another way to implement it. I read about it on the previous stream. As far as I know, most people do it that way, or direct access table. But bit vector also requires on time for clearing. What is bit vector? Is it like bitmap? Bit array. A bit vector, also known as a bit array or bit set. Yep, it's bit set. It's that structure that completely stores Boolean values using individual bits here. How do I use bit set for that? This is a canonical next level for ECS. A sparse set uses to raise sparse, indexed by entity ID, stores the location of the entity's component in a dense array. Oh, I see. So we store just not the component but just the ID. Indexed by entity ID, stores the location of the entity's component in the dense array, tightly packed array of actual component data. Yeah. Okay. Okay. This gives you a one lookup and tightly packed, cache-friendly iteration. Yeah, it's more contact learning experience. How's it called? Bit set? Yeah. I saw a lot of people using bit set, but I don't really understand how does it solve the problem of indexing components. Okay, so this one is interesting. So I firstly index sparse and then I index dense with the result of sparse. But also I don't really like the ugliest thing is that I have to, damn, I got 800 dropped frames, that's unfortunate. Anyway, components are hard-coded, right? That's not what I want. The problem we are trying to solve, in our simple ECS from the previous example, our movement system looked like this. Maybe position, world, get component, yep, maybe velocity, if maybe position, okay, yeah. Imagine you have hundreds of thousands entities, but only 50 of them can move. This loop will, yeah. A check will fail. You're doing a lot of pointer chasing and branching just to find 50 entities you actually care about. Yeah, this is very inefficient. The goal is to create a filter to instantly know if entity is interesting to our system before we try to fetch its component data. This is where the bitset comes in. Okay, I guess I kinda see it. The bitset solution, a signature for each entity. The core idea is to assign a unique flag, a single bit, to every component type. Partition bit 0, bit 1, bit 2, bit 3, okay, and so on. Okay, give each entity component mask. Each entity will have an integer like U64 that stores all of its component flags combined using a bitwise or... Okay. And so we just compare integers, right? So we generate this number, this mask, from the components we want to index and just compare it. This integer is the entity component mask or signature. Entity 0 player has, yep, its mask. Basically everything. Enemy, okay. Scenery position. System define a query mask. A system also creates a mask representing the components it requires. Okay. Position velocity. The match is a bitwise check. Now for any given entity we can check if matches the system query with a single lightning fast CPU instruction. Let's see why this works. Okay, yeah, I mean, yeah, this kind of this. This check is greatly fast, it avoids all the pointers lookups and if-else chains. It's a simple integer comparison. How to implement this? But then, like, I have to start. It's like looks so bad. I'm not gonna lie. Okay, but this approach requires to hard code all components. How can I... Damn, how do I write? How can I allow to use any kind of component? To add any kind of component. Let's think. So probably I need the world, right? I need the start called world. Then I probably will have, like, I see it, like, this is a problem, right? I store everything in one struct. However, I want to progressively edit. Oh, a minute. I can use arrays really, right? Probably not. However, if I'll use array of any type, it might be possible, but is it how you should do it? Time generated world. It kind of makes sense. The strategy from hard-coded struct to generic container. The world will no longer know or care about position velocity specifically, it will only know how to manage a collection of component storages. Here's our two-step plan. Create a generic component storage. We'll make a generic struct that can store components of any single type. This will encapsulate the array list logic. Create a generic world. This world will be parameterized at compile time with a list of all component types it should manage. Okay, it would contain a tuple of our component storage objects. Okay. So basically we got entity, component storage, takes the type, return struct, allocator. Where do we get this allocator from? Init? Okay. Components. Array list. Okay. The init ensure capacity, set self components, items, entity component. Okay. Get mutable pointer to component. Okay. Now we have a reusable generic box for any component type. Component type position is a type that stores. Yep. The fully generic world. This is where the compile magic happens. We'll define world that takes a tuple of types as a parameter. world, any type. Time if type info type of components not equals struct or components len equals 0. Compile error. For components, wow, we get the struct. If type info not equals type, compiler components tuple must only contain types. Wow, what were we doing then? Struct? No, wait, wait, no, I misunderstood it, right? So so that's a tuple. We are going through tuple and checking if all of them are type. Okay, that probably makes sense. Allocator, next entity ID. Storages, this is the core data structure. It is a tuple where each element is a component storage for the corresponding type in components. Init storage undefined. No, actually I don't quite understand. Type of init storages? Where do we even get init storages? Right here? This is the one? Undefined. Helper function to create this tuple of storages at compile time. After. What is after? Wait a minute. ZIG after. Type. That's not ZIG. This ain't ZIG. It's like C++ or something. Tuple. Len any type equals undefined. Line form. Should I use just ready to use ECS? Last week. Okay, we got structures, ECS, register init, allocator, entity, register create, register at entity position, velocity. Okay, it looks so good. Create and iterate a view that matches all entities with velocity and position component. Okay, create view with velocity and position. Iter. View entity iterator. Iter next entity. Okay, so we just taking the view entity iterator. Okay, that's interesting. Position get const velocity. Okay, the same example using an owning group and iterating with each. What is owning group? Registry. I'm curious about registry. Registry. Handles, components, contexts, groups. Okay, that's a lot of stuff. Group data. Man, that's a lot of stuff. Okay, actually I'll leave it for tomorrow.